Welcome back to another video. If you're new here and you don't know who I am, my name is Jesse. I am a tutor in Melbourne and I make videos for GAMSAT. I sat in March of 2021. It was actually my third sitting. I sat a couple of times a few years ago, back in 2012 and 13. This time around, I achieved an 84 and a 100 in Section 3. And so what I do is, given my tutoring background, I figured I would make a bunch of free resources on YouTube to help people prepare for Section 3. There's obviously a huge need for it, and unfortunately most of the resources that are available are all paid. And in this one, we're going to be going through a bunch of sample questions that I've written up that hopefully reflect the actual ASA material for Section 3. I've already put them up onto my resources page, which I'll link below. So if you do want to do them first and then watch this through as a worked solutions video, then by all means go ahead. You can also pause the video and then give it an attempt and then click play and kind of see the worked solution as I work through them. The other aim for this video is not just worked solutions, but also to kind of show how I would tackle a particular question. It's a little bit tricky because obviously I've written them myself, so I know where they're headed. So I've written them in a way that they use a bunch of different problem solving techniques or methods to kind of cover all the different ways that I looked at questions in Section 3, and that helped me then achieve the score that I did. Okay, so what we're going to do first is go through here. I've got Unit 1, and this is set number 4 on the resources page now. We've got the half-life of a drug is the time required to reduce the blood plasma concentration of the drug to half of its original value. Recently, studies have demonstrated that a more accurate parameter in pharmacokinetics, bit of a tongue twister, is the terminal half-life, which is defined as the time required for the blood plasma concentration to reduce by 50% after it has reached pseudo-equilibrium of distribution. So there's obviously a lot of jargon in there, right? So the first thing that I would be doing is kind of making note, and obviously you can't highlight on the new computer test, but maybe make notes on the scrap paper if you needed it. Is we've already defined the half-life. For me, I would look at that and go, okay, I'm already familiar with that concept, right? The second part, though, it then talks about a terminal half-life, and that is a new term. So we can see here, it's still talking about reduction by 50%. So I'm going to link that to my knowledge of half-lives, but clearly it's differentiating it from a standard half-life. It says that this is after it's reached some pseudo-equilibrium of distribution, which truthfully, if I hadn't written this question, I would have no idea what that meant. I'm sure many people right now are thinking, I don't know what that is. Either it'll be defined in the question if you need it, or else you can kind of get past it by just using the term without really knowing the specifics of what it means. It just becomes a handle or a reference within the question. So then we've got terminal half-life can be calculated as, so obviously really important. But again, let's just jump straight to what the variables are. We can see a natural log of 2 and lambda z represents the slope of the terminal phase, which again, a whole lot of stuff that we're not familiar with. So we're just going to kind of make note of that for the moment. And then the terminal half-life has also been shown to depend on the volume of distribution, VD, and plasma clearance C, and so can be calculated according to the equation blah, 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 right? So two different ways to calculate them. So we'll pay attention to these formulas. The next thing then, it goes on for quite a bit. We've also got the figure below represents the steady state that can be achieved by multiple drug dosings over a period of 8 days. And we've got a graph here. I've referenced it if you wanted to go there, but I would probably recommend not clicking the link right now because some of the answers may be revealed if you read through the original article. But if you're interested, because it's quite an interesting study, then you could always reread the original source. So we've got here, again, with graphs, I've mentioned this before, I usually don't read them too heavily. I look straight to my variables so I can see I've got time in days, concentration being measured, makes sense. And then I've got 3 different graphs. So we've got 24 hours, 12 hours, and infusion. And it says here, a drug was administered using multiple dosings I've got to change that, 12-hour and 24-hour intervals. So now I know what they mean. And as well as with constant infusion, over an 8-day period. A lot of little typos again. So now I know, right, so 12-hour interval, 24-hour interval, and one that was just constant as well. And then we've got additional info. So here we go, pseudo-equilibrium of distribution. It's now defining it for us. So is the state after which a drug's concentration initially declines after administering due to distribution to the kidneys, but the total amount of drug in the body remains the same. So that's a lot, that's quite heavy. I'd probably just make note of where that definition is, and anytime I'm going to come back to the pseudo-equilibrium, I'm just going to refer to that if I need to double check. It's also helped us out by saying the natural log of 2 is 0.693. They always do this in the ACER questions. They don't expect you to be able to really accurately work with decimals, approximation if anything, but there's no need to memorize the natural log of 2 or anything like that. They've always defined it. And then we've got volume of distribution measured in litres is defined as the amount of drug in the body it should be, divided by the plasma concentration of the drug in milligrams per litre, and then plasma clearance in litres per hour is the volume of plasma passing through the kidneys per hour. You might, if you've done physiology, already be familiar with that, but again, this is first year biology, so they define that for us as well, or I've put that into the question. So if we go to the questions now, which of the following is true regarding terminal half-lives? So we've got a bunch of different statements. I'm just going to go through and check the validity as we go through each one. So terminal half-lives are shorter than half-lives. So obviously that's to do with this terminal half-life formula here, either this one or this one. And there was nothing in there really about them changing. So both of these measure terminal half-lives. Half-life was just the time required to reduce the blood concentration down to half of its original amount. This one was the same kind of concept, but it was after some distribution had occurred. So there's no information telling us about the actual time interval as to whether it is shorter, longer, or equal. So that immediately just rules out the first two. And maybe you might want to put them in the maybe pile and not rule them out immediately. But in this case, I would be going probably not the answer. I'll look for something that's more correct, that has more evidence going for it. Then we have the terminal half-life of a drug is measured in hours. So with that one, that's a units question effectively. So it becomes more mathematical. So here, this one was a natural log. This here just said the slope. So that doesn't really help me because I don't have any units to work with. I know it's in some kind of time, but I don't know whether it's in hours, seconds, minutes, or days. So the graph might be a little bit misleading because it says it's measuring things in days, but it doesn't necessarily mean the half-life is measured in that unit. If we look to this formula though, we can see this has no units. The volume of distribution was defined in litres and the plasma clearance was litres per hour. So really I can already see that the time unit is in hours, but let's just prove that. Litres divided by litres per hour, and that would be litres times hours per litre, effectively, to divide by a fraction. The litres cancel, and there we go. Half-life is measured in hours. So that would be the most correct. And then we can also rule out the last one anyway. High plasma clearance will give a longer terminal half-life. So if you think about it, that would mean that you're increasing this here. That should actually decrease the half-life because they're inversely related in the formula, so they should move in opposite directions. So that would not make any sense at all. Right? High plasma should actually shorten half-life rather than give it a longer one. So that rules that one out. So then with question 2, the slope of the terminal phase. There's a lot of typos, man. I need to fix those. They'll all be fixed on the thing by the time this is uploaded. The slope of the terminal phase is equivalent to, now we saw that word before, it mentioned it here. This was the slope of the terminal phase. And it's asking us to re-express it in another way. And it's linking it to VD, which was the volume of distribution, and C, which was the clearance rate as well. So what we can do here on this one, again, another maths one, I'd go, well, if these two are equivalent, then I can just make them equal to each other. So that means that the natural log of 2 divided by lambda z, which is what we want to solve, should be the same thing as natural log of 2 times VD on C, if I put in the variables. The natural log can cancel because it's on both sides, and we end up with 1 on lambda. I'll leave off the z now just because it's a bit quicker. It's VD on C. So if I want lambda, then I just have to invert everything. So therefore lambda is equal to C on VD, like that. And so that gives me D, and I don't have to check the others. Any maths ones, you can usually just solve them. You don't have to test answers. Then number 3, the half-life of the drug represented in figure 1 is approximately. So we're going to go to figure 1. We're looking for the half-life. So we can see that it was being dosed every 12 or 24 hours. The infusion one is not going to help because we're not going to get to see the decay rate at all because it's constantly being upped. And so if I look at, for example, I'm going to go with this section here because it starts at 100, right? And that's a nice clean number. I know that it should reach 50 after one half-life. And so if I look to what it's gotten to here, for example, that is roughly 50%, or 50, I should say, 50 units, which is half of its proportion. And so that has happened in 1 day. So that would mean then the half-life should be 24 hours. Now, that one's a good example of one where I've just kind of made the question for the sake of GAMSAT. If you actually look at the link, I can reveal now, it actually talks about a 48-hour half-life for it. But again, we don't need to know any of the specifics that might have been explaining that. We just have to look to the graph and be able to read a graph and understand how to work backwards to solve things like half-lives and stuff. Okay, so question 4, if a particular drug is administered to a patient at 10 a.m. and only 25% of its initial concentration in the blood remains at 2, and their volume of distribution is known to be 2.2 litres, an approximation of their kidney's clearance rate would be. So I'm just going to ignore all the typos that are in there and fix those later. So first of all, I'd be looking at trying to draw out all of the key information from it. And so the first thing is I can see here, starts at 10 a.m., and we're recording at 2 p.m. So we've got a 4-hour gap, right? 4 hours. And by that point, it's down to 25% of its initial concentration. So that would represent 2 decay cycles. So in other words, 2 lots of a half-life. So these are going to be equal. So now I know if 2 half-lives is 4 hours, then that means that the half-life must be 2 hours. So that's the information to help me out there. Everything they give you is really just like tools to work out missing information. And sometimes you have to go through a series of calculations to get there. Another thing that you can do is just look straight to what they're asking you for and go, where did I see clearance rate? The only place that it was actually mentioned was in this formula. So therefore you must have to know all the other variables in that formula, in order to be able to solve it. So if we write that down, T half is natural log of 2 multiplied by VD on C, and we're trying to solve for C, so I can just do a switch here, switch these out, so C then is going to equal the natural log of 2 times VD over T half. So the natural log we were given, 0.693, multiplied by VD, which was given as 2.2 litres, all in the correct units as well. And then the half-life was in hours, so that was 2. And then what I can do here is just kind of 0.693, I can equate these as roughly 1. 2.2 divided by 2 is basically 1. And so therefore around about 0.7. If I wanted to be more accurate, it's technically 1.1. So then I can just call this 0.7 times that by 1.1. I'm adding 10%. So 0.77, which is around about 0.8 litres per hour. And there we go. So this then would be A. Like that. And so again, another maths question, you don't have to test every single answer. I would only do that if I had no idea what to do. I was trying to come at it backwards. Whenever you're solving, you can just solve straight to the answer without having to check the others. If you're comfortable with your maths, just do that and then just move on. And the last one in this set is consider the following statements regarding terminal half-lives and steady states. So we've got terminal half-lives are dependent. What I often do here is I skip over this. I go straight to the statement, see if it's true, if I'm looking for true or false statements, and then tick them off as I go. So terminal half-lives are dependent upon dosage interval. So where did I see dosage interval? That was in the graph. So if I look there, I'm comparing these two really more than anything. Did that affect the half-life? From what I can see, no, right? We could actually prove the half-life was exactly the same because on this one, it dropped by about a quarter or so in half a day. And so therefore we could assume that it would drop another quarter because it looks to be roughly linear to half its value in one full day. In one full day like that, which that was giving us that half-life of 24 hours. If we looked at the other one, which we used before, that one was dropping to about 50% in 1 day. So it meant that the dosage interval didn't seem to be impacting it whatsoever. So that one is actually going to be false because it says it is dependent. So that one's out. The time taken to reach steady state is relatively unaffected by dosage interval. So if we look at that there, time taken to reach steady state, which is where it's kind of flattening out. And you can see all 3 graphs roughly reaching it. Here you could say maybe 7 days or so, but there's not really any significant difference. There's a slight difference here, but they're all about the same. So that one actually looks pretty true. because it says relatively unaffected. That's the key word there. So that one's all good. And then a patient with kidney failure will require more frequent dosage intervals to achieve steady state. So this is a little bit linking on existing knowledge of what the kidneys actually do. And that is their job is to filter out drugs, right, from the system. So if someone's got kidney failure, we can assume that they're not clearing the drug as quickly, which would mean linking it to this. There's always going to be a direct link. It means their clearance rate is going to be lower, right? So if they've got a low clearance rate like that, we can see what that does to the impact. What that does is it means that it'll increase, because they're inversely related, it'll increase the half-life, which means that the drug decays at a slower rate in them, which means they shouldn't have to require as frequent dosage because their body's not able to clear it as quickly as the average person. So a patient with kidney failure will require more frequent. No, they'll actually require less frequent in that case. So that one makes that wrong. And so the only answer is 2, making B the correct answer. All right. So we'll move along to the next unit. So this one's quite a tricky one. This is a physics question, or a physics set of questions. Pretty heavy on the calculation. I haven't yet gotten to Archimedes' principle and buoyancy and that kind of thing in the crash courses, but that will probably come up pretty soon as its own isolated topic, because the maths in it seems to confuse a lot of people. So I'll probably spend a lot of time explaining the theory of that, but for now we'll just go through it briefly. So hydrogen gas is a highly volatile molecule that when unpressurized fills a large volume. Given it has a number of uses as a fuel, storage of hydrogen needs to be done both safely and resourcefully. So far I'm not really pulling anything too important from that, apart from the large volume when unpressurized. That may be helpful because I know that in chemistry you've got the gas law and that kind of thing. Hydrogen is commonly kept in pressurized tanks, although the costs associated with this are becoming economically unviable for many energy producers, so they're looking at alternatives. One suggested solution is the storage of hydrogen vessels in the ocean in order to make use of the hydrostatic pressure of the water above it, according to the equation. So we're just going to make note of that. There we've got hydrostatic, where rho is the density of the water, g is the value of gravity, and h is the depth of the water. One issue with this solution is that because, and I wrote helium, I fixed the other ones, but that should say hydrogen. Because hydrogen is significantly less dense than water, in order to submerge the vessel, a weight will need to be placed on top of the vessel to help overcome the buoyancy force, Fb, and that's then defined here using this formula, where V is going to be the volume of water that is displaced by the vessel. And we've got a couple of notes here. So assume that the density of water is 1 kilo per litre as well, and assume that gravity is 10. They often use gravity as 10 because 9.8 is not going to be significantly different enough, and it just keeps the formulas a little bit more simple. The weight of the hydrogen vessel is going to be 2.5 tons, and it has an overall density of 9 by 10 to the negative 5 kilos per litre. That is the density of hydrogen gas, so we're assuming the container is also insignificant or irrelevant. I haven't factored that in. I've just said, let's just take the whole tank as having that density. The vessel will be stored at a depth of 40 meters. So what volume of water will be displaced by the vessel when fully submerged? So this is a bit of a trick question, trying to see if people are going to overthink the Archimedes principle, almost be over-prepared. When we think about it, all it is whatever volume you're taking up needs to be displaced. Because if you've got water already there and then you're putting something in place of that water has to displace to somewhere else. So in terms of volume, nothing's going to change here. It's just going to be the volume that is displaced is equal to the volume of the vessel. So volume of the vessel is equal to the volume displaced. I'll do VD, I guess. And so we are, well, what's the volume of the vessel? We were given the density of the vessel and the mass. So we know that density is mass per volume. So therefore we can rearrange that and we can say volume is mass per density. And the mass was 2.5 tons, which is times 10 to the 6 kilos, over the density, which was all in standard units, 9 by 10 to the negative 5, like that. And this will give us our volume. So if we do this, I would do 2.5 over 9, and then do index laws on these two. So 6 minus negative 5, which is actually going to be 11. And here I'm just going to call that, I know that 3 over 9 is 0.33. So a little bit less than 3 over 9 should be a little bit less than 0.33. So I'm going to say about 0.3 times 10 to the 11. And then I'm going to adjust, because scientific notation should always have a leading number that's between 1 and 10. 3 by 10 to the 10, like that. And there we go. And then that gives me my answer of B. Simple as that. What mass will be required to fully submerge the vessel? So with this one, in order to submerge something, the buoyancy force needs to be overcome. So the force pressing down has to be equal to the buoyancy force. So I know then that the mass of the vessel plus some other unknown mass, right, which I guess actually I'll use X, weighing down with a gravitational force, right, times 10, should be equal to the buoyancy force. And the buoyancy force is this thing over here. So this, ignore the negative, that's just to say it's moving in the opposite direction. So I'm just going to leave that out. Let them equal to each other. And the rho here for water is 1 kilo per litre. The gravity is 10. And then the volume now of the water that's being displaced, because that's what V represented, we know is 3 by 10 to the 10. Like that. So already I can cancel out the 10s. And then I know that the mass of the vessel was 2.5 by 10 to the 6. Right? Plus X. And 1 times 3 by 10 to the 10 is just 3 by 10 to the 10. And so really I'm just subtracting this, but you'll notice it's 4 orders of magnitude smaller. So really, it's actually not going to have any significant impact whatsoever. It's basically still going to be 3 by 10 to the 10. And you effectively have to add that much mass to the vessel. So a lot more than the vessel itself in order to submerge it. And so the answer then becomes A. So it's a bit of a trick question. The others seem like they've done more calculation. A looks almost like the red herring where it's just copied across, but it's just because the other numbers are relatively insignificant to it. And then finally, we've got if instead the vessel was designed such that it could compress under force with a compressive constant of 3 litres per 100 newtons, the new density of the container at a depth of 40 meters will be what? So again, designed to be really overwhelming, right? So we've got compression now and there's forces getting involved. So what I'd do here is kind of draw out a force diagram. So we've got our vessel and we've got to think about all the forces acting on it now. So it's got the gravitational force of the mass that's sitting on it, and the mass was 3 by 10 to the 10. Times that by gravity. Let me do that a little bit more neatly. I might zoom in on this. So we've got the mass times gravity. So that was 3 by 10 to the 10 times 10, which is really 3 by 10 to the 11, pressing down. You've also now, when it's actually at depth, it has 40 meters of water above it. And so therefore there's a hydrostatic pressure applied as well, and that was rho g h. So that is 1 times 10, and the depth was 40. So that gives us 400 newtons pressing down as well on top. And then we've also got the buoyancy force pressing back this way, right? Trying to resist that. And that we did before, which was rho g times v. We found that to be 3 by 10 to the 10. So 3 by 10 to the 10, pressing up. Now the difference is because it's free floating and it's able to compress, all of these forces are actually contributing to the compression. So we don't actually subtract them from each other and get a net force. The net force is actually adding them all together because they're all helping compress the vessel. You'll notice though that the 400 in the hydrostatic pressure is again insignificant in its order of magnitude. It's in the hundreds. The others are in the thousands of millions, so in the hundreds of billions and tens of billions. So the 400s are not going to do anything. So what I'm going to do is just leave that out and say, all right, well, force total then is 3 by 10 to the 11 plus 3 by 10 to the 10. And so an easy trick for this is I can just treat this one. I can scale it up to a times 10 to the 11, but I just have to adjust this to 0.3 like that. And now I can add these two and get 3.3 by 10 to the 11 newtons is the force that's being applied like that. And so coming back to it, this was what's going to be the new density. So it gave us a compressive factor. So compressive constant that said 3 litres per 100 newtons. So it means that it's going to reduce by 3 litres every 100 newtons that is applied. And so then I just have to work out the change in the volume of the vessel. And so the way that I can do that is I can just multiply the force by this compressive constant. And the reason why I know I can do that is because the units are in litres per newton. So if this is in newtons, then the idea is the newtons are going to cancel, and then I should get liters like this. So if we do that, I'll just get rid of this here. So the force was 3.3 by 10 to the 11. That was the total compressive force. We multiply that then by 3 liters per 100 newtons. And probably what is easier is I'd probably go with writing everything in exponential form so that you can apply index laws. So here we can apply an index law between these two, and we can get 10 to the 9 by subtracting 11 minus 2. And then we've got 3.3 times 3, which is 9.9. And this would then be the change in the volume, and this would be a decrease in volume in liters. The original volume was 3 by 10 to the 10. And then we're taking away a loss of 9.9 by 10 to the 9. Now what's easier is this is effectively 10 by 10 to the 9, which is basically 1 by 10 to the 9. And that makes it a lot easier so that I can now go 3 minus 1 by 10 to the, that should be 1 times 10 to the 10. So then now this can be 3 minus 1 times 10 to the 10. So this is 2 by 10 to the 10, and this is the final volume. So then what we're trying to work out is the new density. And remember, density is mass per volume. The mass of the vessel hasn't changed. That's still going to be 2.5 by 10 to the 6 kilos, divided now by 2 by 10 to the 10. And again, I would split this and think of it as 2.5 over 2, and then I would apply index laws between these two here, and then get 6 minus 10 is negative 4, and then deal with this. So this, I would think of this in halves. If I divide both of these by halves, I've got 5 halves fit into 2.5. So 5 over 4 halves fit into 2 by 10 to the negative 4, and then I know that there is 1.25 by 10 to the negative 4. And there we go. So again, as an estimate, where's the question? Here we are. So that then means the answer is going to be C, like that. Cool. All right, and then finally, I just had a bit of like a question that's not a real one. I've put it in there. It's not a real question because you wouldn't really be expected to go through the reasoning like this, but I just thought it'd be a fun one to go through. It does use a little bit of bio at the same time. They never really do many like med-related ones anyway, and this is somewhat like an ethical thing of there's a yes and a no, so we're just going to go through it and think about how you'd reason it. Angiotensin 2 is an enzyme that causes vasoconstriction, narrowing of the blood vessels to upregulate blood pressure. When angiotensin is active, it constricts the blood vessels and increases pressure, which increases the required contractile force of the heart to pump blood. Angiotensin converting enzyme, or ACE inhibitors, are a class of medications that inhibit the action of angiotensin and are commonly used to treat high blood pressure. So in terms of note taking, what I'd be doing is I'd just be writing like Ang2, and then I'd just write, well, actually, no, that'd be a bit confusing. I just write vasoconstrict, and I might put like increase BP, and then I can just put ACE inhib and put a little block on it like that to remind myself of what it all represents. So in a hospital, there are 4 patients with a variety of complications as summarized. A bit like the statements thing, I just go straight to what I need to do with them. How many patients could be reasonably treated using an ACE inhibitor? So we've just got to kind of take this information and look at safety precautions of each one. So patient 1 is suffering from syncope, a condition that involves passing out from sudden drops in blood pressure. So if you were to give them an ACE inhibitor, this would not allow them to raise their blood pressure, which would mean their blood pressure would remain low or lower. And so therefore that would not be good because that would exacerbate the problem. They've got low blood pressure already. We don't want to make it lower. So that would not be a good patient to give it to. Patient 2 is suffering from renal failure in their kidneys and has a below average blood volume level. So if they have low blood volume, that would mean they have low blood pressure. So again, we would not want to give them that. And you can see now we've created a bit of a rule. Now we know that low blood pressure means don't give them ACE inhibitors, because if you give them an ACE inhibitor, that's actually going to keep the blood pressure low or prevent it from being upregulated to fix the problem. So again, we would not want to give patient 2 that particular drug. Patient 3 is suffering from acute angina, a chest pain that when experienced feels similar to a weight pressing down on the sternum or the chest area. So with this one, there's no mention of blood pressure or anything, but it's talked about chest pain, right? And so it mentioned about when you use angiotensin, that increases the force required on the heart. So if there's any pain coming from the heart, you probably wouldn't want to put it under more strain. If we were to use just a basic line of reasoning, just like you, I'm not in medical school or anything, didn't get in this year, so don't take this as medical advice. And I'm sure there's probably things that would say opposite to what I'm going to say, but we're just going to use what we'll call GAMSAT reasoning. And we're just going to go straight on the basic facts and theory that's presented. If someone has chest pain, we would not want to increase the force on the heart required. So in that case then, angiotensin does that. Therefore, ACE inhibitor does the reverse. That should relieve the pain, right? So that would mean that you can increase the blood pressure. So we'll give them that. So if you give them an ACE inhibitor, this will prevent their blood pressure from rising, which will mean that it should stay low, which should hopefully alleviate some of the pressure on the heart itself and maybe fix the angina. I don't know, again. Patient 4 is currently on blood thinning medication after surgery to prevent blood clots. So they're trying to prevent blood clots. They've already got thinned blood. If they don't have the ACE inhibitor, then it means that they can raise their blood pressure. If they do have the ACE inhibitor, it means that they can't, and it means their blood pressure stays very low. In terms of blood clots, you actually would want higher pressure with thin blood, because then thinning it means that you'll prevent the blood clots. Slow moving blood is more likely to clot. High moving blood is less likely to clot. Obviously, there's links to high blood pressure and blood clotting and that kind of thing from smoking and heart disease and all the rest of it. But again, we're just going to use that basic reasoning. Really, you could argue with me on that and say that patient 4 should not be given it because it's just safer to use something else. So really the answer might be 1. I'm going to go with patient 4. Hopefully I haven't killed them or anything, or else maybe I should never be a doctor. That's kind of the reasoning to go through there. So like I said, don't take that one as gospel. That's really not an ACE type question. I just thought it'd be interesting to go through, test your reasoning, and it's more of a reading one than it is a kind of math science one. So a lot of it is based on the words and the kind of qualitative analysis that you run through, which are a little bit rarer in section 3 as well. Cool. All right, there we go. That's everything. So 9 questions. I'm trying to keep them relatively short and bite-sized so the videos stay pretty short for the worked solutions, but as we build them up, there'll obviously be more and more. If you're looking to do more of them, maybe you could wait a couple of weeks to let a few bank up, and then you could do 3 in a row and have maybe about 30 questions or so, and do it as a little mini test and then watch the videos to practice. Hopefully these, again, have been helpful. Leave me some feedback because I want to keep improving them as we go. And so, I mean, already I'm trying to change up the questions based on the feedback and that kind of thing. But if you think that there's a particular area that has not yet been covered in one of these walkthrough videos, then let me know. If it's content related, let me know, and that will go into the crash course videos. I'm trying to keep them very separate, where this is about strategy and question answering, and pacing and that kind of thing, whilst the other one is really just about the general underlying principles and theory without as much question-based analysis in them. Other than that, I don't really do outros or anything like that, so I'm just going to leave it there so it doesn't drag on, and I will see you in the next one.